So immediately, sort of, you can equivalently express the flow as the flow of a metric and a two form B, which is potential for H. So the time derivative of G minus B, there's some funny scientists. In any case, the time derivative of G minus B is minus twice this Ricci tensor, where now the time dependent H is the background H plus dB. Okay, so plus dB. Oh, hi. Is it better? Okay. Okay, sorry about that. It's just like a roof top for people online. So I just want to start by just pointing out that this flow right off the bat will hit a broader classic fixed point. So it's just a nice excuse to introduce an example which plays a key role in a lot of the results I'll talk about. So if K denotes a semi-simple group, and you fix a binomial metric G, and then I let H denote this Cartan 3 form, which you can define for left invariant vector fields using the Lie bracket. Okay, so H, X, Y, Z is just the inner product of the bracket of X, Y with Z. Then it follows that these associated, I kind of already changed the story a little bit, Bismuth connections. So now I have two where I look at both plus and minus of one half G inverse H. They're both flat, actually. They're both flat connections. And it's a very old result of Cartan skeleton. Well, this is, they prove more than this in any case, but they do exist. That all Bismuth flat structures are quotients of this construction, and actually a sort of much more, I guess, tractable to modernize sort of proof was given by Agricola. And just sorry. You can and then like a very elementary example of this construction is where K is S2, S3, G is the round metric, and H is probably some multiple of the volume form, the standard volume form, and then this will be flat. So already we see sort of a friendly face, this round metric on S3, but appearing in a very different way from how we might usually think of it. And so already you can see in this example, you might expect this flow to behave very differently depending on the cohomology class of H. So when H is 0, we all know the round metric is a Ricci equation back to time, but for H non-zero, in particular, if H is DS3, the round metric is fixed. So this geometry is just fixed under this generalized Ricci flow. And somehow, in a certain sense, it's protected by the cohomology class of H, which is preserved by the flow. So yeah, so again, just to set the stage, I'll sort of ask some very, very broad questions. So what new sort of topology or geometry might we expect this flow to detect? And what sort of topological geometric significance can we assign to the torsion H? So right now it might feel sort of tacked on. And moreover, what is the relationship of this flow to complex geometry? Because of course this interaction between Ricci flow and Taylor Ricci flow is incredibly rich. Okay. So and again, the point of view I'll take, well, what I believe is sort of the more or less only real point of view is that the answers to these questions are sort of the right way to think about the analysis of this is through this new field of generalized geometry, which is a sort of field that's recently emerging in recent years that's sort of really kick-started by this foundational work on generalized Calabi-Yau. What he calls generalized Calabi-Yau geometry. I guess this terminology is not so much in favor, but in any case. And so I just want to just briefly explain what this connection is. And then we'll sort of come back to it later in a more concrete way in the complex setting, where I'll show how it really genuinely influences the analysis. But so Jürgen's talk very briefly discussed this object of sort of generalized tangent bundle and the Courant bracket. So E is just a vector bundle T plus T star, and E comes naturally equipped with these two objects. First is the neutral inner product. Defined here is this symmetrized contraction here. And then also we have this bracket structure here. So x plus c brackets with y plus eta to be this perhaps strange looking combination of operators. But in any case, these are some natural operators that we're used to, derivative, interior product, exterior differential, whatever. But also the construction allows for a natural twisting by a closed three form. Again, there are sort of conceptual underpinnings to these, but I won't really get into that, why one would do this. But in any case, it's a natural bracket structure that you put on this bundle, which is some kind of extension of the Lie bracket. Okay. So with the idea that how does the story of Riemannian start? It's a manifold, we have a tangent bundle, we have the Lie bracket, and then sort of attached a metric G, the dimension which incorporates sort of the smooth structure in the sense of the bracket with some other conditions. So here we want something similar, and we're going to define a generalized metric. So a generalized metric, G is a orthogonal such that when you lower the index axis, that higher individual product, you get a positive and you can combine this in your algebraic story, and you get this essentially equivalent to a pair of a standard Riemannian metric G and two more B. And then the orthogonal G is expressed as follows. This is natural orthogonal G. So this is star, but then conjugated by G. And you can find out this is okay. So we have sort of structure, bracket, we have a metric. The next question I want to ask is what's a natural dimension? What is the sort of story? Because it doesn't seem to be an analog of the generalized metrics. You can impose natural dimension involving torsion, but it does not quite pin down one dimension, but there's reasons for that. Yeah, identified class dimensions, which have natural properties. They have distinct curvature tensors, but they have single region tensors. So the natural region tensor is the same for all of them. And somewhat interestingly, so I briefly introduced this relationship again, because it's more of a star. And you notice it's actually involves each other of both of these dimensions. So there's H going around, which is a background T plus B, or T plus metric. So that's giving us two disconnections, and they both here. This is sort of reality is and with this point of view, and again, this is all this is just a calculation at this point. You could rephrase the slope, which I think is all here. Okay, just express naturally as an evolution relation of generalized metrics, since it's that Ricci flow for these generalized metrics. Okay, so we have a little bit of metric motivation. But now we can, that's what we actually do. So I just very briefly recall some fundamental regularity problems of the flow. So some basic adaptation of the Hamilton's gives you short time solutions in general on. You can also prove that solutions exist as long as you have actual Riemann system. As long as the geometry G is controlled, H is controlled, and everything's controlled. And then sort of more interestingly, what goes on, generalized gradient flow. Okay, so here I wrote this functional. Precisely one function. This one extra. Yes. So can H blow up the mount? And very roughly, the reason is because so that connection is the positive magnitude but it is a concept of particular so yeah, so we have this functional script F, so which is this and then you find so you take the and the theorem from 2006 of the generalized Ricci flow is a great for this line. So it's precisely this thing that Ricci flow is a great for So okay, so here's some basic irregularity, but then maybe what can we say globally? Okay, so the first dimension where we can expect this flow to differ from Ricci flow is 3, right? So I have a 3 form. The only place that the first place that I have 3 forms is 3. Well, we can still sort of get a flow which is relevant to Riemann surfaces by dimension reduction. Okay. So let me describe this ansatz. So I start with a 3 manifold, which is a principal circle bundle over a Riemann surface sigma. And I fix a metric on sigma and a principal connection on M, call that mu. And then I can define an S1 invariant metric on the total space in the usual way. So this is like define ansatz and pull back G plus mu times mu. You get an S1 invariant metric on the total space. And then I can get the curvature of mu, call that F. So I'm using the abelian structure here and suppressing some identifications, but in any case, F can be identified with a 2 form on sigma. And then I can define a 3 form. It's some specific ansatz, so I can take H to be F wedge mu. DH is of course 0 just by dimension reasons. Okay. And the point is that the generalized Ricci flow preserves this ansatz. Okay, so it preserves this sort of relationship of H. It'll first of all preserve the S1 symmetry and then also preserve this form of H. And then, excuse me, this generalized Ricci flow expressed as sort of it's a metric flow coupled to a flow of the 3 form is now a flow of this metric on the Riemann surface, which is Ricci flow, coupled with the Yang-Mills term. So F squared, that's the Yang-Mills energy, and then mu is just evolving by Yang-Mills flow, where again the G is of course the time. Okay. And this appeared in some. This is what I did in my thesis on. It's Ricci Yang-Mills. Well, right, yeah. That's a good point. It's too late now. Yeah. Okay, but so excuse me. In this ansatz, we get a complete description of the flow. So this is the theorem from earlier this year. So maybe I don't have to really say this part. I'm just repeating what the ansatz is from the previous slide. And we get the following 4 statements. So if the Euler characteristic of sigma is negative, then we get global existence of the flow. And then I can take this blowdown limit. So I'm taking the total space M, taking the metric on M, the capital G metric, divided by 2t. So this is the natural sort of blowdown scaling. And it will converge in Gromov-Hausdorff sense to the base space sigma, to the base of the vibration, with the canonical metric of constant curvature minus 1. Okay? So the fibers all collapse. The fibers are collapsing. Okay? If the other characteristic is 0, then the flow exists globally. And again, this flow down limit will converge into all Hausdorff sense to a point. What's the okay, yeah. So so it's a little bit delicate what precisely. So at least conjecturally, in all cases, it should just converge to yes. Actually, I'm offhand forgetting exactly what I believe here, but I think in case 1, they certainly can prove that at close to concept, and I think I did not prove in case 3 and 4. But yeah, so there's actually a couple of technical questions left in that. Or what I mean is things one would want to know furthermore about the flow besides the fact that
with the genus positive and the constant curvature like on the next one on the line on the action a flat circle one. There's still an interesting question whether that converges. Even if you know its curvature can converge to a constant.
Right. Exactly. Yes, that's right. Yeah. So yeah, we get sort of a complete picture of the, I guess, the metric convergence that we have. Okay, but then, well, maybe before going to items 3 and 4, I just mentioned that this, of course, is basically exactly what you see for regular Ricci flow. It's kind of not really anything new yet. So if you just sort of forget that you even have this bundle structure, and the F is 0 trivial bundle, F is 0, the Ricci flow is doing exactly the same thing. But then for a positive genus, we see something really sort of new and interesting, where the topology of the bundle plays a decisive role. So if other characteristic is positive, but the first term class of the bundle is 0, so the bundle is trivial, then it will have a finite time singularity. And then when you do this natural sort of what's called like type 1 blow up, so if you blow up the singularity of type 1 rate, you get convergence to sigma cross R. So now the fibers are blown up, and and you get well, so I guess I only stated it as convergence by time slice, but the whole space time will converge to this standard shrinking ancient solution. Shrinking down. And then most interesting of all is when you have positive other characteristics but non-trivial bundle. And so here, what you get something genuinely different. So the flow exists globally, so for all time, and converges to a quotient of this Bismuth flat structure on this. And so, this, you can kind of guess this roughly just by computing like the evolution of the volume, say, of the Riemann surface. And you can decisively see the way the first term class sort of stops the volume from going to 0. Basically, the volume controls so much on Riemann surfaces that plus a lot of regularity theory is enough to prove this. But that's really sort of why, or how it enters in a sense. It's just to show that the volume. So you really see something. I mean, here you can really see what I was kind of saying before, which is that the sort of the topology. I mean, in this case, on the total, here the topology is clear. It's just the first term class of this bundle. But in any case, the cohomology class of H is the same thing here, right? So the cohomology class of H will be non-zero precisely in case 4, whereas it's 0 in case 3.
So you're assuming that the initial data is circle invariant.
Yeah. It's
but that's really the essential thing.
Yeah. I mean, that's
the quotient is finite quotient.
A finite quotient. Yeah. Okay, yeah. So I'm going to take sort of a hard detour.
Are you not able to reduce the question to Ricci flow?
No, 100% no. Definitely not.
So in the last case, you have a sign for C1. Does that determine whether it goes to the right or left invariant? It's sort of imagine solutions of reflections of each other.
Probably.
Reverse the circle action.
That's that's true in the sense that the solutions were, yeah. So you can take, yeah, in general, I guess you can take a solution like GH or G naught H, starting at G naught H naught or G naught minus H naught. And I guess that's preserved. The metrics will be the same, and the time dependent free forms will remain different by signs. Probably that's true. Yeah. Yes.
So when I see the condition that the form
Right.
So is that one of the reasons why this case is more tractable? Is that going to cause problem in higher dimension?
I'm not sure. I mean, in a way, yes. I mean, I guess what you're saying is it buys you something in higher dimensions. Doesn't really buy you. Yeah, it's all.
Well, it doesn't have that. It might be hard.
Or, you know, it should even like find an initial condition in the first place. Well, sure. Yeah, like I guess if you want to genuinely change the behavior you see for each flow, you want it to be non-zero.
We want not zero, but you want those to your approach.
100%. Yeah. I mean, I think there. Yeah, you can define extensions of the flow to where H is not zero. It still makes sense. Sorry, not close. It still makes sense. But in my setting, the whole talk H is close. I would doubt that this is preserved. If this was, but yeah, it's interesting. I've not tried.
Have you tried just turning a little away from circumvariance?
Not particularly, but yeah, but of course it's reasonable to expect. Well, okay, I guess I do have a student trying to work on general stability at the business class. So yeah, he basically was. But yeah, probably should hold for these other cases too. Of course, it's part of. Okay, so yeah, so maybe I'll sort of move on now to the relationship to complex geometry. So yeah. So as I said before, of course, yeah, this story of the interaction of Ricci flow and Kähler geometry in the form of Kähler Ricci flow is extremely rich and interesting. And it turns out you can sort of extend that story to complex manifolds using generalized Ricci flow, more general kinds of complex manifolds using generalized Ricci. So yeah, so we already had this definition once today, but so if I fix a Hermitian manifold, MGJ, we call it Pluriclosed if I take DC omega, I call that H, this is the natural DC operator, and then I just ask that H be closed, okay? So we call Pluriclosed, also strong Kähler torsion. Yeah, and so this is sort of the only natural linear integrability conditions where once we move past zero. And there's this well-known result of Pluriclosed, which tells you can construct Pluriclosed metrics on every compact complex surface. And maybe I just sort of mentioned sort of general analytic remark is that you cannot expect this to reduce to a scalar or something like that. Like there's not really a deep bar lemma. They simply are just they're not described that way. Pluriclosed metrics in general locally are described by a 1, 0. So you can find local potential 1, 0 points, but that's as good as it can do. Okay. So it turns out that there's, I'm going to sort of take a brief step away and then come right back to generalized Ricci flow. So there's a natural geometric flow of Pluriclosed metrics that we call Pluriclosed flow. So here I just briefly write it down how it looks in sort of like a local description of the flow. So I'm flowing now the Kähler form, where here you see this friendly term, which is like the first term H in curvature, so I d bar long term G. But then it's further modified by d star omega minus d bar star omega. So that's some further term like this. And in any case, you can just check that locally this operator at a Pluriclosed metric probably looks like the coordinates of the G or possible. The point being that you can construct solutions, short-term solutions. But then to bring it back, what does this have to do with generalized Ricci flow? So again, I call H dc omega as before, and I let theta be the Lie form. So yeah, we saw this before as well. So there's d star omega composed of J. That's the Lie form. then there's this theorem with myself and Tian from a decade ago now. So if I fix a solution to this Pluriclosed flow, then I get associated metrics, three forms H and V forms. And then the point is that they're basically evolving by this generalized Ricci flow. So the GDT here, we see this generalized Ricci flow, but of course there's the gauge term. So we drew the term involving the V form, that's theta sharp, that's hard to see. And then the free form H is evolving by the usual heat equation, but then again, it's gauge modified. In this sort of canonical way, it's not just, I don't know, it's coming to in a particular gauge, if you like, using the okay. Thus, a different way to think about it is that, well, this generalized Ricci flow, it preserves Pluriclosed, sort of, but only after you think about it as you're also flowing J. So if I want to pull this all back to look like generalized Ricci flow, then I also have to pull J back. And so J will now have an evolution equation, which once you pull it back to the generalized Ricci flow gauge is like a heat equation for J. So you kind of have to couple to an extra equation for J to actually get ultimate return. Okay. So yeah, so we know it's essentially generalized Ricci flow, so we have these basic regularity properties, but so then now we can ask what sort of global behavior might we expect on non-Kähler surfaces. Well, of course, the flow can be studied on any complex or on any complex manifold emitting Pluriclosed metrics, in particular all Kähler manifolds, but maybe it's better to focus on non-Kähler ones. That's sort of the whole point. So again, as a starting point, I'll mention this old result of Godeshan-Ivanov. So if I fix a compact complex surface, this is not exactly how they stated, but this is what they do, or it's equivalent. So G is Pluriclosed and satisfies basically that it's a fixed point to the Pluriclosed flow. Okay, so I have this modified Einstein equation. So this is the usual Riemannian Ricci, then 1/4 squared, and then this gauge term involving the V form. Similarly, I have the D star H. So here I'm kind of down one variable. I don't have the equation for all crossing. I have just the star H and minus the interior product of theta star H. This should all be. So it's some sort of elliptic system coupling the Einstein equation with the equation of H harmonic. Now what they prove is either H is 0 and it's Flavial, or you get a very special example. So the M4J is not just the Hopf surface, but it's a so-called standard Hopf surface. So it's a quotient of C2 minus the origin by a dilation by complex numbers alpha beta, which have the same norm. And the metric is a product of the round metric on S3. So those manifolds in particular are diffeomorphic to S3 cross S1. And so then the metric is a product of the round metric on S3 with this standard metric on S1. And then H is dB S3. So in fact, this is just like the example from the beginning of the talk with an extra S1 factor now. This is the only genuine fixed point for this flow of complex surface. Okay. Yes, okay. I have sorry. Yeah. And so, well, okay, so this Hopf surface, we have this nice fixed point, the standard Hopf surface, and we might expect the flow to perhaps converge to that. What else is going on in the world of complex surfaces? Well, I'll just mention a few other facts. We know that actually a lot of other non-Kähler complex surfaces tend to arise as elliptic vibrations. So non-Kähler surfaces of quadratic dimension 1 are vibrations, and in fact, only multiple fibers occur, and you can take a finite cover, which is a genuine T2 model, over a Riemann surface, which in this case will have negative order characteristics. Similarly, quadratic dimension 0, the non-Kähler examples again are vibrations and only have multiple fibers and are finitely covered by a T2 bundle over this time of Riemann surface of G is 0. And so, as it turns out, also invariant Pluriclosed metrics on these surfaces are exactly in the ansatz I described before. And so also I stated the result for generalized Ricci flow for circle bundles, but in fact it holds, you can prove basically the same statement for torus bundles. So the only this sort of dichotomy is just in the case of the sphere, it's just whether or not the bundle is trivial. And then of course again, quadratic dimension negative infinity, these standard Hopf surfaces are of course also principal.
So after you pass the cover, you could actually take it to S1 times the 3 manifold.
That is also true. So the upshot is that at least for invariant metrics, this theorem from that I mentioned for 3 manifolds, in fact, immediately has a corollary for complex surfaces. So let me maybe just maybe I just bring it all on the screen right now. So these are basically the same 4 cases as before. Case 1 is the case of this is like the higher dimension one, which is T2 bundle now over a 3-month surface of negative Euler characteristic, and then 0 Euler characteristic, and then case 3 is the complex manifold of S2 cross T2, and again here you get a finite singularity, a finite time singularity, and the type 1 blow up converges to S2 cross R2. But then the case of like non-trivial bundle over S2, the only case, well, really at play here is this standard Hopf surface. And it proved that every porous invariant flow exists globally, and again converges to a multiple of what I'm calling here the Hopf metric. But again, this is just the same flat S3 structure across S1. So it's really, like I said, the earlier results sort of immediately gives this because these Pluriclosed metrics are automatically in that onset. Okay, so yeah, so we have some nice description now of this flow for cases of symmetry. But what about moving past that? Okay, so now I finally want to get to something very specifically complex geometric, and so I'll sort of discuss some new result where we can like remove the symmetry hypotheses for some of these results.
So this question, this symmetric hypothesis, you don't assume some local value.
No, yeah, the metric is invariant. Yeah.
Only invariant.
So yeah, so to discuss these new results, I want to give sort of yet another formulation of this Pluriclosed flow using the holomorphic Courant algebraids. So here's really where the sort of generalized geometry point of view has some real payoff. So what we discussed in our paper is essentially due to this old paper of Bismuth proving his index theorem on non-Taylor complex surfaces. Okay. So we fix a Pluriclosed metric omega naught. We consider this holomorphic vector bundle Q, which is T10 plus lambda 10. And then we define a twisted D bar operator. So D bar, oh, that subscript tau is the type. This should be like L omega naught. It's supposed to indicate that. In any case, this twisted D bar operator is defined using the metric omega naught. So D bar x plus C. So I just take the usual D bar operator on T10, the usual D bar operator on lambda 10, but then there's this extra term involving the sort of torsion of omega naught. So if omega naught's scalar, of course, nothing's happening to it. But in general, it's different, and the Pluriclosed condition is precisely the condition that it's actually a D bar operator that squares to 0. Okay. That's exactly what
But it's only changes D bar on lambda 10.
Well, if you like.
Oh, no,
it's really kind of hard to see.
Yes.
So now I want to fix like another. So this omega naught, I fix sort of a background Pluriclosed metric. That's defined as a bar operator. But now I want to fix another one where the torsion class is the same. Okay, so del omega minus del omega naught is d bar of a 2-0 form of beta. Okay, and then I define now this Hermitian metric on Q, which ought to look familiar. So this is very similar, of course, to the sort of generalized metric from the beginning of the talk, but now sort of in the holomorphic category. Although I guess here I've written it genuinely as a metric as opposed to an endomorphism, but up to sort of an index with shift using neutral inner product, it's basically the same. Okay. So this is a Hermitian metric on this holomorphic vector bundle, and it has a Chern connection. So there's no sort of funny business here with the theory of connections and curvature, right? So I immediately get a Chern connection. It has a Chern curvature, and then it has a contraction, which I call the Hermitian-Yang-Mills curvature, S, or S, upper S, superscript G. And then the sort of fact, which is amazing to me, is that this curvature like vanishes precisely if you have what is this vanishing condition, which is vanishing of the classical Bismuth Ricci curvature. So the metric G, the Hermitian metric G downstairs has this Bismuth connection, which is a Hermitian connection. And its Ricci form vanishing is precisely the right-hand side. But now we see it's equivalent to this sort of Hermitian Mills type condition for this generalized metric, capital G. Okay. And not only that, the metric solves Pluriclosed flow, which, of course, maybe I just have to say that in turn induces an equation for the 2-0 form beta. You can attach an evolution for beta as well. And once you do that, this generalized Hermitian metric capital G is basically evolving sort of by Hermitian Mills flow. But of course, there's like a sort of a small y in there because defining this Hermitian Mills curvature requires a metric on the base space, which of course is also evolving now. But in any case, in some formal sense, it's like a Hermitian Mills. Okay, and so using this point of view, we give this is joint work with my student Josh Jordan and Mario Garcia Fernandez from this year. So we can sort of extend this theorem from before to the case without symmetry. Okay? So the first theorem, we fix a compact complex non-Taylor surface of non-negative two-variable dimensions, so 0 or 1, the only possibilities. I fix any Pluriclosed metric, then we prove it exists globally. We do not prove what should be true, which is that the blowdown limit behaves as it does in the symmetry. That's what one would expect. There's no reason it should not be true, but we don't prove that. And then in the case of the standard Hopf surface, again, we fix an arbitrary Pluriclosed metric. We prove the global existence of the flow and moreover convergence to the Hopf metric. So here again, there's no symmetry involved at all. So we prove in general that this one, again, there's a unique non-Kähler fixed point of this flow, and it's globally attractive for the flow on that manifold. So it's a very satisfying result in that. Okay. So, and again, the proof relies crucially on basically, so a lot of Kähler-Ricci flow theory involves these applications of parabolic Schwarz limits to get control over the metric. And I just say that it's sort of, in a sense, it's similar to that theory, but it's all done with this generalized metric G. Of course, all of these computations in the end, I imagine, could be sort of boiled down. You could kind of pretend like you never knew anything about generalized geometry and prove it, but it would probably be extremely opaque. Whereas it might be quite easy to see from this generalized point of view why it's true. Okay. So, all right, so that's maybe a fairly satisfying picture for some of these complex non-Kähler surfaces that I mentioned, but there's still a lot more. So there's non-diagonal Hopf surfaces, class 7 surfaces, parabolic in a way, hyperbolic, etc., etc. There's quite a large scene. So what can we say? Well, yeah, so based on this Perelman monotonicity and some optimistic conjecture making, you might expect it to converge to a solid. So again, these equations appeared in Yuri's talk. And these are just exactly the Euler-Lagrange equations for this F functional restricted to a fixed cohomology class of H. And so, yeah, so if you don't really expect any kind of singularity formation in finite time, well, maybe it exists globally, maybe it converges to a solid. By this monotonicity. And so sort of based on this, yeah, this part I can maybe go over very quickly. Luckily, I'm following Yuri's very nice talk. So in 2018, using this kind of point of view, we said, well, they should maybe exist on these class 1 Hopf surfaces. So this also may be like diagonals, the terminology. But anyways, these are Hopf surfaces when you quotient by diagonal. Matrix diagonal. And so we proved that these steady solid forms do exist on all of these class 1 Hopf surfaces. And then later with Yuri, we sort of derived them much simpler way using this T3 invariance and prove they have this bonus structure from generalized Taylor. Okay? And then also, as you discussed very nicely, we joined with Bessie and Yuri, we proved the automorphism and scaling. So this, in fact, gives again, as Yuri mentioned, a complete answer to the existence and uniqueness questions of solutions to this, to this natural system of equations in the complex set. They're either Calabi-Yau or they're these special metrics on Hopf surfaces, which again, I should just maybe emphasize, they form a nice family with this Hopf metric. Okay, so like as you change the moduli parameters of Hopf away from the standard ones, the metrics form smooth. And maybe I just also mentioned to connect to the beginning is that all these structures, in fact, do have a product structure with S1. So in fact, they're all pullbacks of structures from S3. So in fact, even forgetting all the complex geometries, so on S3 with this standard flat structure on S3, there's again a family of solid structures. All right, so that's the compact case, but then what about the complete case then? Because again, this is obviously not capturing the whole story, right? So these things provably only exist on Hopf surfaces, and so there's still a lot more, even though we covered some more cases. Again, one should expect the flow to converge to these solitons when they exist, but there's still a lot more, so maybe they converge to some complete solitons. All right, so in the last 15 minutes, I'm going to say as much as I can about what we can say about complete solitons. So again, I guess a lot of this I can sort of really already explain nicely. So yeah, so here I just briefly recall the definition of generalized scalar from the classic point of view. So it's a bi-Hermitian triple, Gij, and then I have this perhaps unusual looking matching of the two torsions off the sign, they have to be closed. And then in dimension 4, sort of generically, they come equipped with this symplectic form. So Yuri only mentioned, well, really the Poisson tensor is the more fundamental object, but I'll just go ahead and ask that it be invertible, and then look at its inverse, called the big omega is G as the inverse of the commutator of I and J, and it turns out that it's type 2002 with respect to both I and J, and it's holomorphic. That the I20 part is I holomorphic, and the J20 part is J holomorphic. And basically, the whole structure can be recovered from this symplectic triple. So in the locus where you have this description, omega and then the I imaginary and J imaginary parts give the whole structure. And in the case of a hyperkähler manifold, this is just the usual hyperkähler is what you're talking about there. And then sort of surprisingly, there's, well, a classification, at least a sort of maybe a rough classification in part at the moment of complete generalized Taylor Ricci soliton. So with Yuri last year, we proved every complete four-dimensional generalized Taylor Ricci soliton either admits a toric symmetry, so that's still a sort of a black box at the moment. I think we already mentioned this, but we're sort of working on this case, or it's described by this generalized Gibbons-Hawking ensembles. That's just some words. Let me say. So to build up to what this Gibbons-Hawking ensemble is, I'll just recall some general structure. Okay, so I don't even really need generalized Taylor yet. Just fix a Hermitian structure, Pluriclosed, and impose this soliton P. So you can just do some computations and prove that this vector field 1/2 theta sharp theta is the leaf form minus grad f is holomorphic, and JV is Taylor. And again, this is something very familiar from sort of Taylor Ricci solitons. So there'd be no theta, but it's the same. You get a holomorphic vector field such that the action J on it. So for a generalized Taylor Ricci soliton, right? Basically, the point is I have this system of equations in two different ways. Once with respect to I, and once with respect to J. So you get two killing fields, IVI, JVJ, where it's this vector field from above, but in two different senses. Okay? You get two killing fields. Basically, the point is either they span generically a rank 2 distribution, that's the toric case, or they're aligned. Okay, so they're multiples of one another. And if they are, then what you found is a biholomorphic killing field, right? So it now preserves everything. Right? So there's one vector field that preserves all the structure. EIN. And so, well, that's precisely the setup of given talking nonsense, right? So if you have a hyperkähler manifold with a triholomorphic killing field preserves everything, then you get this beautiful construction of given talking. So we can generalize that to this setting. So again, I'll fix a generalized Kähler manifold, and this triple of symplectic forms where big omega is as defined before. And let me just assume that it exists a free isometric biholomorphic S1 action generated by a vector field X. Okay? Then we can immediately, I guess I also want to assume it's Hamiltonian in any case, so Ix big omega is of course closed, but I want it to be exact. I want all these forms to be exact, so that I can define these functions, mu1, mu2, mu3. You can check that the mat mu defines a submersion to a domain in R3, but we want to sort of recover the geometry somehow in the image of this moment. Okay, and the key quantity for doing that is the so-called angle function. So this function p is -1/4 some factor times the trace of the product of I and j. But this is basically, because it's by definition, the inner product of I and j. Okay, constant. This function is less than 1 in absolute value, and it's constant if and only if the structure is hyperkähler. Of course, p being constant equal to 0 is what we're thinking about in neutral hyperkähler. But as long as p is constant, then I and j will belong to hyperkähler. Okay, so this function p plays a key role. So as in the given talking concept, I need to sort of keep track of the length of x, and the right way to do it is to actually define W to be gxx inverse. And then the quotient, the geometry of the quotient space can be described explicitly. So in terms of mu1, mu2, mu3 coordinates, you get this explicit description of the horizontal geometry using the function p and these coordinates mu. And it looks, well, in any case, we introduce these new coordinates mu plus and mu minus involving this mu2 and mu3, and it looks a little bit more symmetric. Let's just do that. So you do get an explicit description, but actually so far all we used was the generalized Kähler condition and the symmetry, and the function p so far is arbitrary. And yeah, sorry, actually. So furthermore, by analyzing just the generalized Kähler condition, you get, so in the usual given talking concept, the function W has to be harmonic, right? So the quotient metric is just Euclidean, and that's worth mentioning too. The case p equals 0, of course, instantly reduces to the usual Euclidean metric, is what you expect. But so now, and W would be harmonic, but now, well, it satisfies a linear PDE, but it has this perhaps funny looking extra term involving the angle function. Okay, it's a little bit obtuse at the moment. Okay, and then of course the construction is also reversible in the sense that if I just define a function p and a metric as written, and a function W that satisfies the PDE, then I can get a generalized Kähler metric out of this. I can reverse the whole thing and uncover the G.
So there's another direction that's suppressed here. You're talking about social geometries.
Yeah, I'm only describing. Yeah. Mm-hmm. But yeah, so far it's not rigid, right? So the hyperkähler setting, just by definition, it's already rigid because, well, you already have your Einstein equation. But in this case, there's plenty of, so like, for instance, as you already described by this flow construction, you can take these structures and form them in dimensional space, and you can change this p to be, you can deform the function p sort of arbitrarily. But of course, that's where the soliton equation comes in. And so again, there's sort of like a scalar reduction of the soliton equation, which fixes p. That's the point. So we have these two soliton vector fields as defined before. And again, I'm imposing this hypothesis that they span a one-dimensional space. So that I have my biholomorphic filling field. They generate an action. Then I can express Vi and Vj as some multiples of Ix and Jx. So those are like moving in the horizontal space now. And it's a general fact of generalized scalar geometry that the difference of the Lie vector fields is always Hamiltonian for this canonical Poisson structure. And the precise formulation is as follows. So notice Vi minus Vj, the grad f drops out. And what you get is, in fact, the difference of the Lie forms. And then that, in general, is the omega inverse E capital Phi, where capital Phi is a functional transformation. So it's essentially equal to the angle, but Phi equal to 3 minus infinity. So thought of differently, these vector fields Vi and Vj fixed together with the idea that omega, capital omega is fixed. 3 is P for them. 3 is the function. And in particular, sort of just unwinding those definitions, you can express it explicitly in the moment map coordinates. It's just whatever these two constants are, ai mu2 minus aj mu3, and then we define some different constants, a plus minus, with respect to these better coordinates plus minus. Okay. So yeah, so phi is just a linear function of these two momentum vectors. So now up to the choice of these constants a plus minus, we have p. Once we have p, well then we have this metric h that I wrote before, at least we have it much more concretely now, at least on this non-degeneracy locus. So again, varying all this story is that I'm assuming that omega is non-degenerate, okay? that it's genuinely simple. So this sort of finishes, if you like, the local analysis of this Solomon equation. But okay, but now we have to sort of globalize the whole story. And so to do that, to actually produce these examples, there's sort of 3 interlocked problems that you kind of, well, you sort of solve them. Yeah. So yeah, so I didn't emphasize too much, but yeah, so luckily, if you're going to find the sigma, which is really G inverse of the commutator Ij, and capital omega is the inverse of that. But in general, sigma will have a degeneracy locus. So already, right, in the case of Hopf surfaces, it's like this standard Poisson tensor, C1, C2, delta Z1, delta Z2, which has degeneracy loci on the 2 standard complex planes. So it will degenerate, and we have to remove that to get the Stephen Hawking picture, and we have to lift the universal cover to make sure that the action is Hamiltonian. Okay? So how can we sort of extend this moment map globally over the degeneracy locus? So that's one problem. Another problem is that you sort of quickly realize that these metrics H as expressed here appear to be incomplete. Of course, that's maybe to be expected once you know you remove part of the manifold. But so in any case, 1 and 2 are sort of linked issues. We've removed the degeneracy locus and H is incomplete. And you sort of look, well, in any case, we end up proving that the completion locus is precisely the vanishing locus. And then, of course, we also have to produce and classify the choices of W. And so again, this is a delicate part of the hyperkähler story. You have to prove, assuming that the metric is complete, the hyperkähler metric is complete, you know that the image of the moment map, we have to prove this, is all of our 3, so that then W is a harmonic function, a globally defined positive harmonic function on R3, and then you finally have a classification. And you know it's the superposition of and so, yeah, so I don't, I guess, really have time to explain it in much detail, but I just want to show this picture, which I try to explain as much as I can. So what this is supposed to be is a picture of the 2 possible images of the moment. So there's some constants in the picture. So this K plus is a 2 over A plus. Remember that these 2 parameters, these 2 dials in the story, A plus and A minus. K plus is 2 over A plus, K minus is 2 over A minus. Which might be infinity. And if it's infinite, that's where we get this first picture, okay, where the angle function P is allowed to go to 1 on one end, and that is the degeneracy locus of the Poisson tensor. Whereas, okay, let me explain this first picture first. So what this is supposed to be is it's a 2 orbifold. So there's an orbifold singularity mod 1 D2 mod DK plus. But there's a product of that with the real line. And then the orbifold point, the real line passing through the orbifold point will be the degeneracy locus of the Poisson tensor. That's where the angle function goes to 1. That's where I equals j. So the two complex structures align on that locus. Well, and then you're allowed to have poles of this function W. So it turns out that this space as drawn will generally be with an explicit Riemannian metric can be sort of completed. The metric H that I wrote down before can be completed on this space, and then you have to sort of take a further conformal modification, and you see that this equation for W turns into a Laplace equation, that conformally modified metric. And so finally, you can get some Liouville theorems and get like a classification of these W's. The upshot being that, again, there's sort of a superposition of Green's functions. So you're allowed to have some poles, which gives some further topology to the format. So
these functions are in positional symmetry.
only in some very special cases. Yeah. So like basically, if you have no poles, then there's some extra symmetry. Yeah. But whenever there's poles, there's no extra symmetry. Oh, yeah.
Your formula for d-ative there is just suggests that we have
Oh.
that expression would not be closed. You have
Yeah.
counter terms to get closed.
Exactly. Yeah, exactly. Yeah. So as it sort of comes to you in terms of this metric H, it doesn't look particularly clean.
There's
You
some
have to make it.
the second is very
But in the end, by making like a further conformal modification to this metric on this 3 orbifold, right, you can convert it into a Laplace.
So are the poles always the green function type? Or is it something more complicated?
No, yeah, it's precisely.
Just one of the two wrong.
Exactly. Yeah. Well, and yeah, and that's just coming from the fact that we're trying to just find a smooth, like the fact that you must complete the smooth format forces this. Okay, yeah. So so one of the cases. This is the case where one of those two parameters, a plus minus, is 0. But in general, where they're not 0, the image of the moment map is this like spindle. So it's a product of this well-known like spindle metric on S2, which is this orbifold. So I have orbifold points at the end, one modified, or one modeled on the disk mod of ZK plus, the other disk modulo ZK minus. But then it's a product of all that with R. But then now you have like both degeneracy loci, one where P goes to 1, where I equals J, one where P goes to -1, where I equals -J. Maybe I got my sign. Anyways, yeah. So you have these two degeneracy loci. And again, for instance, the universal cover of the Hopf example is contained in this type 2. I mean, precisely there's actually no orbital points. It's just genuinely the round sphere, a product of R, and no poles. But yeah, and then again, the sort of classification of these W's comes down to like elliptic theory on a particular conformally modified metric on this thing.
That would be the description of the universal cover.
Yes, yeah, universal cover. But yeah, okay. Thank you. Thank you.
I really like the fact that you fit both this Phoenician story and more general things into the same picture. So it's really the same flow. So when you look at these flows for, let's say, elliptic surfaces, elliptic non-Taylor surfaces, you get exactly the same flows as your sort of simpler case and for 3 manifolds times the circle.
Yeah.
And you can show that those are like, if you take something which is torus invariant on that those are the most general solutions.
Sorry.
So I mean, you could so the simplest case there would be when you actually have a T2 principal bundle and or I'm sorry, a T2 bundle, and then you can look at T2 invariant metrics as your initial data, and I guess there must be an extra constraint on what's the H, but it's probably built in just by.
Yeah. So yeah, in the Hermitian setting, this extra ansatz of H is F wedge mu is automatic from the Pluriclosed condition.
And so now it just reduces down. You have a circle that's left alone. is that right? And then-
Yeah, okay, yeah, sorry. In the general T2 case, it's like a sum of H will be like F1 like V1 plus F2 and V2.
I see.
Yeah. And that is the precise form of Hermitian metrics. That's the form of torsion.
But there's a trivial circle bundle built into it.
It is there, yeah. So you're right, of course. That's not really necessary, I guess, to start the story. But of course, you are right. You can, if you like, assume that yeah.
So in terms of the kinds of solitons you end up looking at, you're basically looking at the steady ones. Is there any analog of shrinking or?
Okay, yeah. Well, all we have are strong non-existent results. So for instance, on complex surfaces, well, first of all, even sort of defining what you mean by shrinking soliton, using this Ricci curve, it's not always completely, I'm not always convinced it's so natural, but any definition you impose immediately implies that they're a party. So yeah, and there are several results in this effect. So shrinking soliton by some definition is automatic. And there's actually a very general result in the expanding setting. So the expanding setting, even just like the Riemannian world, expanding generalized Ricci soliton is automatic. So yeah, I think again, it's something sort of, if you like, talk about. So it's not how you to shrink, right? Because the class should be somehow this is what is why and this.
Are there some other questions for in presence room? Perhaps I will ask somebody from the Zoom room if there are some questions. Seems not. Let's thank the speaker again.